Okay, today we're continuing 8.6, which is the area between curves with multiple intersection points. This is still in general just area between two curves, but we're getting a little bit more aggressive here. So in this case, really what we're looking at is this region R bounded between the function y equals that, y equals 1 and y equals 2. So if we had the option to right minus left here, that would be great. However, the problem is this curve that we'd have as the right and this curve that we'd have as the left are part of the same equation. And so that's usually not a great thing if we're trying to split the equation. So instead, we're going to have to do this in terms of x. And we always want to think about it as top minus bottom. And so to do that, we're going to have to split it up into three separate little integrals. Now, one of those integrals is going to be this little triangle here, where I see this top curve minus 1. Then we have this rectangle in the middle. And then we have this other little kind of curved triangle right here. So one of the good things about this, however, is that this graph is symmetrical, which means that this area and that area are going to be the same. So if I can figure out what that intersection point is, I can really just do 2 times that integral from 0 to whatever that top bound is, and then use that to help me figure the rest out. So we do have Calc active, so I'm going to just graph this real quick. And graphing this, I find that that bound is point 0.25 to 25226. 226. And I'm going to do top curve, which is this e to the 3x minus x squared, minus my bottom curve, which in this case is 1. Again, I'm doing the 2 times because I'm saying that this area and this area are the exact same. Then for this rectangle, I know the height of the rectangle is 2. And then this width is what we're trying to figure out, which is going to be this 2.5226 all the way up to this intersection point. And that intersection point is 2.74774. So 2.74774. And so what I can do here is just add this rectangle of height of 2, width of 2.74774 minus 0.25226. And again, we are able to do all of this in our calculator. So this just becomes pause it real quick and see if you can put that in Desmos to do it. So take a second and try that out. So I threw that into Desmos and I got 5.222. Now, another way you could have done this, again with that same idea of symmetry, is you could have done this as like 3 minus. You can kind of see this wedge shape here and this wedge shape here. You could have said essentially that this is 3 wide and 2 tall, and done 6 minus double the integral from 0 to 0.25226, and then taken 3 minus this lower curve of e to the 3x minus x squared dx. This will get you the same area because really all we're doing is saying, hey, take the bigger rectangle and take away these little 2 tiny triangles, whereas the other way is kind of adding the 2 triangles to a smaller rectangle inside. But either way, this one is definitely for sure Calc active, unless I wanted to do a setup. And if I wanted to set up, I'd have to give you at least one of the intersection points. Okay? All right, let's on to the next one. So here we have these equations, and you're given this picture of a graph. We do need to figure out how we can slice this in a meaningful way, so that way we're able to maybe separate the integrals if we needed to. So one of the things I like to do here, especially if I'm given my graph, if you can sketch it out, that's great. Try to bound your solution to help you out. So one of them is f, which is this quadratic. Then we have g, which is this blue curve. And then we're also told we have x equals 0, which is essentially the y-axis, y equals 0, which is the x-axis, and this other bound of x equals 2. And so I'm finding this area right here. See if I can change this. This area, that's not helpful. This area right here. There you go. It's kind of highlighted. That looks like garbage. Oh well. We're going to just try to find our area between that region, which means we need to think top minus bottom and then maybe split it potentially. This isn't a great case for doing it horizontally because again, we notice here, like if I try to do it horizontally, I would not only have to do it like, I'd have to split here, then there's this weird overlap like here potentially. And then now this right here, super gross. Let's not do that. Instead, let's just try to do top minus bottom in terms of dx. So if I'm setting this up, I realize that up until 1, our graph is going to look something like the integral from 0 to 1 of f of x minus 0. Now, I'm actually going to take a second and integrate this one. So I'm just going to do top minus bottom dx. And then from 1 to 2, now we have to deal with this line. And so I'm going to have another integral, which is 1 to 2 of f of x minus g of x. What I've done here is I have taken it as this area plus this area. And that's really what I'm trying to find, the area between those curves. If this is a setup but don't solve, please feel free to use like f and g. You don't need to actually like fill in those equations. But in this case, we're going to, because I'm going to simplify this down and evaluate. Before integrating, I'm probably simplifying this down to x squared minus 4x plus 5. And then I'll integrate. This left chunk is going to become x cubed over 3 minus 3 over 2 x squared plus 4x. Evaluate that from 0 to 1. Plus, and then this is going to become x cubed over 3 minus 2x squared plus 5x from 1 to 2. Plugging the 1 in, I get something like, let's throw this up here. Plugging the 1 in, I get something like 1/3. Oh, it's blue. Minus 3 halves plus 4. And then plus plugging the 2 in, I get 8/3 minus 8 plus 10 minus plugging the 1 in, 1/3 minus 2 plus 5. If this is calc inactive and on an FRQ, I would expect you to just box that bad boy up and call it a day. If this is actually like a multiple choice question, you do need to simplify this down. I'm getting something like this and this add up to 9 over 3. So just 3 plus 4 is 7. So 7 minus 3 halves. And then it looks like I'm doing a plus 2 from these two. And then I have minus 1/3 minus 3. So I'm getting 6 minus 3 halves minus 1/3, which we could change this into 2/6 minus 9/6 with a 36 over 6. So I get 27 over 6. 25 over 6 is the final answer. Isn't that gross? That's gross. We love it. Again, this is why I suggest if calc inactive FRQ, leave it as that. You box here, right? You integrate it, you roll, you plug in your stuff, you call it a day. Okay? That's the first half of this question. The second half says, is the height of A increasing or decreasing? Okay? So is the height of that increasing or decreasing at 1.5? Now, it's important we say at 1.5 because 1.5 means we're talking about this parabola minus that line. If I instead said something like 0.5, it would just be the parabola minus y equals 0. But here, the height is these two functions, f and g subtracted. Now, what's the key calculus word here? Increasing or decreasing. I say increasing or decreasing. You say derivative. That's right. So we're going to subtract these two values and then find the derivative of the height. The height here is going to be f minus g. So we're going to take x squared minus 3x plus 4 minus x minus 1. That's our f minus g. So that'll end up being x squared minus 4x plus 5. And then we take that derivative. So this will give us 2x minus 4. This is f prime minus g prime. And now all we have to do is plug in 1.5. So that's going to give us 3 minus 4, which is less than 0, therefore decreasing. And I probably want to label this as like f prime of 1.5 minus g prime. So f prime of 1.5 minus g prime, just for those nice labeling points, equals. But regardless, we found that height is decreasing. I think, like, looking at it, you guys could probably be like, well, yeah, if I look at 1.5 versus like 1.6 versus like 1.7, it kind of looks like that height is getting a little bit smaller, especially if you look at compared to 1 or like 1.2. But the math is showing us that based on looking at the derivative of f prime minus g prime. Okay, let's move on to the next one. So, similar problem here. However, we are now told that our region is bounded between f, g, and y equals 0. So kind of off the graph here, but essentially we realize that this is our region, starting at 0 and ending at 2.5542. Now, again, not great to do horizontally here because we see this red overlapping with itself. And both of these equations are already solved for like y equals, so don't make it harder than you need to, okay? If we're trying to find this area here, we don't have to worry about splitting because the red curve is always on top of the blue curve in this case. So this is just going to become the area or the integral from 0 to 2.5542, and it's going to be f minus g dx. We can integrate that real quick to get negative cosine x minus x squared over 2 plus 2x and plug in those bounds. However, you don't really have the ability to plug in 2.5542 in a meaningful way, so don't worry about that piece. This one again is asking, is the height increasing or decreasing at 2.5? I think you guys could see that height's going to be decreasing, but let's talk about the math behind it. This is just going to be f prime minus g prime, which is going to be cosine x minus 1. And so we would then just be able to say, well, f prime of 2.5 minus g prime of 2.5 is equal to the cosine of 2.5 minus 1. And you might say, well, Mr. Erb, how do I know that that's negative, for example? Well, the best version of cosine we can have is cosine of 0 or 2 pi. That maximum value of cosine is just 1. So anything less than that maximum value, right, of cosine of 0 or cosine of 2 pi is going to be smaller than 1. So when I subtract 1 from it, I'm going to get a negative quantity. So we'd say, therefore, decreasing. I like on problems like this to actually like look at the drawing and be like, does it look like it's getting smaller? And then using the math to kind of back it up. Again, seeing that key phrase of increasing or decreasing. All right, let's get a little bit more weird. Okay, so now we have a function, h of x. H of x is equal to 6 plus this integral from 0 to x of f of t minus g of t dt. We're asked to figure out h of 1, h prime of 1, and h double prime of 1. Okay? For this one, to find h of 1 is just equal to 6 plus the integral from 0 to 1 of sine of x minus the quantity x minus 2 dx. That's going to be equal to 6 minus cosine of x. We could do this a couple ways, but I know a lot of you just feel more comfortable with minus x squared over 2 plus 2x. And then I'm going to put parentheses around this whole thing because that's what I'm like evaluating from 0 to 1. Plugging the 1 in is a little bit gross because it's just 6 minus cosine of 1. Oh, that's weird. Hold on, sorry, gang. Oh, the whole thing crashed. That's nice. Give me 1 second. Sorry about that. Whole thing crashed out. But essentially, we get to here. Now we're just plugging in the bounds. We can simplify this a little bit to make that 9 minus a half or 8.5 minus cosine of 1. But that's really all you can do. There's not really anything else you can do to simplify h of 1. H prime of 1 is actually a lot easier, though, right? So h prime of 1 is going to be the derivative of this integral. Now, the derivative of 6 is going to go to 0. And so we're just really doing the derivative of this integral. We have to worry about this bound and, chain rule. Do we have to worry about it? But in this case, not really, because the bound is just x. So with the bound being x, all we have to do here is make this just f of x minus g of x, which means h prime of 1 is just equal to f of 1, which is sine of 1, minus, and then g of 1, which is 1 minus 2, or negative 1. So final answer, sine of 1 plus 1. And again, I got these values. Like this is just f of 1 minus, and then this is g of 1. And that's all we got to do. For h double prime prime of x, well, that's going to be the derivative of this. So that's just going to be f prime of x minus g prime of x. So f prime is equal to cosine. So that means h double prime of 1 is equal to cosine of 1. And g prime of x is just equal to 1. So minus 1. And that's your end answer. And there you go. That's all you have to do for that one. Pause the video here and see if you can attempt the second one. Okay. Oh, for the second one, m of 2 is just going to be me plugging 2 into here. Oh, hold on. This should also be an x, not a t. Sorry, gang. M of 2 would be equal to 4 plus the integral from 0 to 2 of f prime of t dt. Well, dx. And so this is going to look like 4 plus f of 2 minus f of 0. We know f of 2 is just sine of 2. And f prime of, f of 0 is just 0. So final answer for m of 2 is just going to be 4 plus sine of 2. For m prime, we have to take the derivative of x squared, which is going to be 2x. And then the derivative of this integral, again, nice bound. So it's just going to be f prime of x. Plugging 2 in is going to give me 4. The derivative of sine is cosine. So 4 plus cosine of 2. And lastly, m double prime is going to be equal to 2 plus f prime prime of x. And that's going to loop us back to negative sign. So m prime prime of 2 is going to be equal to 2 minus sine of 2. And that looks super gross, gray on purple. Anyways, sorry for some of the technical difficulties, but I hope this explains enough for you guys. Again, you have practice, more practice on the website that will help you out. Have a good one.